Welcome to the CCEM webinar. I am Yuchen Chen. I hope you are having a wonderful time in the middle of this autumn season. I am a relatively new staff at CCEM, and my career has been consisting of operating TEM to perform material analysis and operating FIB to make TEM laminae or TEM foils. And now at CCEM, I'm mainly operating TEM. Therefore, today, thanks to you, we are having this online session together with a focus on electron diffraction in a TEM. Unveiling materials in reciprocal space unveiling materials in real space from reciprocal space. So the emphasis is laid on unveiling materials and how to by using the electron diffraction. That being said, this webinar is not very generalized on electron diffraction. Just imagine if you have your sample and its diffractogram at hand. How could you analyze the diffractogram? That is the information in a reciprocal space that extract and interpret the information from it, just to unveil your sample, which is in our real space. If you are in this direction, which means you use electron diffraction as a tool or already have some basics on it, you are looking forward to solving material problems with it, this webinar is for you. For those who found this topic too specific but still need to use the electron diffraction, you are encouraged to sit along with me because we are going to solve material problems live in this webinar. So it will be more intuitive to go step by step with me rather than dig the methodology, the applications, etc. all alone. Page. As previously mentioned, what this webinar is about and who it's for, I am assuming optimally you have the prerequisite basics on electron optics, Fourier optics, and crystallography. But do not worry if you don't, because you can nurture yourselves with those books. And it is a very good idea if you revisit my colleague Carmen's webinar on YouTube. I left the link here. Her webinar on TEM basics and practical aspects covers the basics I'm mentioning here. As I said, this webinar lays emphasis on material characterization using electron diffraction. We will go through case studies, and the examples and the results are from the Department of Functional Materials as FZU, the Institute of Physics of the Czech Academy of Science, which is my previous employer and my previous research team, which I regard as my second home, and I feel in debt and grateful to my ex-supervisors and ex-colleagues. Here I put the link to my previous research team, and you can check the website for publications and trends. Unveiling the materials using electron diffraction, that means we will extract and interpret the materials information from a reciprocal space. That is to say, to analyze the diffractogram. I will operate the software CrystalBox for this purpose during the webinar. The software CrystalBox is also from FZU. It is developed by my ex-colleague Mila Klinger. I must say the CrystalBox is one of the jewels of the crown at Department of Material Analysis of FZU. I have been using it daily, and I saw many of you are using it too. So it was a good surprise for me when I left Czech for Canada and found out that CrystalBox is so popular here in our electron diffraction community. I left a link which will lead you to the new version of CrystalBox. The new version has significant improvements, which I personally appreciate a lot. And I think it will upgrade your capability of doing the electron diffraction analysis. So do not hesitate to check it out. Here is the outline of the webinar. Firstly, we are going to elaborate on the electron diffraction and the relation between reciprocal space and real space. These are the backgrounds of this webinar, and they will be presented in a mathematical way, because when indexing and interpreting diffractograms, we are basically doing mathematical calculations. So it is better to bring about the backgrounds in mathematical language. But do not worry, because the fun part follows. Even though I said indexing diffractograms is a process of pure mathematical calculation, nowadays the indexing is computer-aided. So in this webinar, I'm going to run the software CrystalBox and index some typical diffractograms. I'm using the newest version of CrystalBox, so I'm not only covering the classic usage of this software, but also showing the new features of this sophisticated analytical tool. It will be very beneficial for you to acquire this method in CrystalBox. At last, we are going to unveil the materials. We will see in examples how diffractograms and their indexation could do for us. What mysteries in our material could be interpreted from diffractograms so that the mysteries could come into light, and we use the results, the outcomes to prove our hypothesis, to prove our proposed mechanisms, and furthermore, to nurture simulations. So let's begin the introduction to electron diffraction. I bet you all heard that electron diffraction happens because the electron beam interacts with the materials. But how? Let's see a simple scenario. What happens when an electron beam passes through an atom? Here we have an atom, we have an electron beam K0 passing by an atom. The nucleus and the electron cloud has Coulomb potential, which bend the trajectory of the electron beam. So here again, this is our atom. This is the incoming electron. It interacts with electrostatic potential, contributing from both nucleus and electron cloud. The electrostatic field acts as an electrostatic lens. Then questions: in Fourier optics, what does a lens do? In Fourier optics, a lens performs Fourier transformation. The Fourier transformation creates a space, the Fourier space. It is also called reciprocal space. So in here, in a reciprocal space, which was opened by the Fourier transformation. So here we see the fancy F, which stands for the Fourier transform. We got the Fourier transform of the electrostatic potential. It is called the electron scattering factor, the FEL. FEL interprets the ability of an atom to scatter an electron. For example, if it is a heavy element with an electron beam passing through it, you will get more electrons being diffracted. If the scattering angle, the 2 theta, increases, less electrons are diffracted there. And if the energy of the electron beam increases, less electrons could be diffracted. That is to say, more electrons tend to transmit through the atom, ending up in a direct beam without being diffracted. Then, what happens when an atom beam passes through 2 atoms? And this is the electrostatic potential of the biatoms. What we gonna get in the Fourier space? The Fourier transform of the biatom's electrostatic potential. So here we saw the results consists of the summation of the Fourier transform of the 2 atoms, the first atom, the second atom. The both parts contain the electron scattering factor. We knew from the previous slide that FEL depends on the Z value. It depends on what atom it was. The second atom, which is at the relative position A, away from the first atom, produce the phase shift. The summation of the two parts gives the interference of the two diffracted waves. So actually, in the Bragg's law, the 2D sine theta equals lambda is hidden in this formula. If the A here satisfies the Bragg's law, this exponential will be 1. So constructive interference will occur for these two diffracted waves. So you see here, even though we are not writing the Bragg's law explicitly, it is still here, hidden in this formula. So in mathematics, we can use different formulas to describe the same thing. Now think about a real scenario. What happens when the electron beam passes through a group of atoms? The result of the Fourier transformation is still simple and concise. It will be in the summation of the electrostatic potential's Fourier transform of each and every atom times the exponential function containing phase shift or the relative position among atoms. So here, the xi, yi, zi is the coordinates of each atom inside this material. Or we can see the coordinates of atoms in our real space. The hjk is the coordinates in reciprocal space. So if at a certain space in reciprocal space, say hjk and all the xi, yi, zi satisfy the Bragg's law, we will get a diffraction spot at that hjk position in the reciprocal space. Don't worry if you find this is abstract, because we are going to see an example together. But before that, think about this question. Does this formula suggest that we really have to consider each and every atom inside our sample? That might be exhausting. To answer this question, let's see what a unit cell is. This is the simulation of a group of aluminum atoms. You can see inside this group, there is a small cubic unit. If we replicate this unit, stacking them from front to back, up to down, left to right, you will get this group of aluminum atoms. And the smallest repetitive unit is called unit cell. And the structure of the unit cell is called the Bravais lattice. For aluminum lattice, it has a FCC, face-centered cubic structure. And certainly, different crystalline materials may have different lattices. There are 14 possible Bravais lattices showing in here. Remember that we are still talking about the scenario. What happens when an electron beam passes through a group of atoms? So instead of considering each and every atom inside our sample, we consider the unit cell and its lattice structure. And let's continue with the FCC lattice of aluminum. Let's see what happens when an electron beam passes through this FCC lattice. What we get in the Fourier space or the reciprocal space. At first, let's consider how many atoms do we have in this FCC lattice. We got 6 atoms on the faces. They are shared by neighboring 2 lattices. And we got another 4 atoms at the corner. They are shared by the neighboring 4 lattices. So in this FCC lattice, we got 4 atoms. And these are the coordinates of the atoms. They are the Miller indices for crystallographic points. Remember the summation of the Fourier transform of each atom. Let's put the coordinates of the 4 atoms inside and we get a result in reciprocal space. The math tells us that if the Miller index in a reciprocal space, the HKL are either all even or all odd, we will get constructive interference. That is to say, a diffraction spot. So let's play with the Miller indices. Those are all even HKL, and this is an odd HKL. At those coordinates in a reciprocal space, we have diffraction spots on it. If we put those HKL into 3D reciprocal space, what we get? A reciprocal lattice. And can you tell what its structure is? A body-centered cubic. Yes, if we have a FCC structure in the real space, we get a BCC structure in a reciprocal space. And what is the link between the real space and the reciprocal space? The Fourier transform. I must say that the reciprocal space is a real existence. It is as real as the real space we are in. So for example, when an electron beam shines on the aluminum materials, it has a FCC structure in the real space. Diffraction spots in the form of BCC structure will appear. Remember, it is a 3D problem, so the dots you see here are actually this reciprocal lattice in 3D dimension. And you see here, they are in layers. The ground layer called zero Laurent zone, the upper layers called first order Laurent zone and second order Laurent zone respectively. But the diffractogram that we get through a camera is in 2D. So here we draw a Ewald sphere, which has a diameter of the reciprocal of the electron beam's wavelength. Here, for example, the Ewald sphere cuts through zero order and first order of the Laurent zone. So this is the geometry that will appear on our diffractogram. We got the zero order Laurent zone in this circle and the first order Laurent zone in this ring. And do you remember that we said the Fourier transform links the atoms in the real space and the diffraction spots in the reciprocal space? So if we tilt or rotate our sample in a real space, its reciprocal lattice will rotate too. That means if we view the sample from different perspectives, if the electron beam comes in different directions, we will get different geometries on the diffractogram describing the same material. So let's take the aluminum as an example. The FCC structure in real space, and let's view it from different directions. So if we view the lattice in the real space from 100 direction, we will see the atoms on the 100 plane. And on the diffractogram, we are viewing the reciprocal lattice from 100 direction too. So this is what we get on the diffractogram. It is basically replicating the spots on the 100 plane of the reciprocal lattice. If we view the lattice in real space from another direction, say 100 direction, it is the same philosophy, viewing the reciprocal lattice from the 100 direction. Let's change the viewing angle again. The direction 111. Same thing again. We will be viewing the reciprocal lattice from 111 direction on the diffractogram. Here is a more intuitive image, which is made by Mila Klinger, the author of Crystal Box. The left side is the unit cell of magnesium. If we rotate and view it from different directions, its diffraction patterns change too, accordingly. So when we work on a diffractogram, it is not only essential to index each diffracted spots, but it is also crucial to identifying the zone axis. That is our viewing direction here. Let's come to the practical part to index the diffractograms. What geometries we could get on diffractograms if you put your selected area electron diffraction or SAED aperture over a single crystalline material, and it is in a zone axis, you will get dotted diffraction pattern. If you have multiple lattices into zone axis inside SCED aperture, you will get sets of dots. For example, here we have two lattices in zone axis. We get two sets of diffraction spots. If multiple lattices or multiple orientations are present, you will get discontinued rings depending on the texture of the material. If even more lattices and orientations are engaged, we will get a ring pattern that is less discrete and more wide. And if the material is amorphous, you get continuous rings. So the geometry of a diffractogram depends on the crystallographic structure, the orientation, the texture, etc. of the material. And here is a GIF image made by Miller again, based on the diffractogram of magnesium oxide. At the very beginning, we just have a set of diffraction pattern from one grain, which is just one set of dots. And as the number of grains increases from 1 to 1,000, the dotted geometry turns into rings. Because when you introduce more grains, you introduce more orientation and textures. So we have dots at the beginning and ends up with rings in the end when we increase the complexity of the texture. Here I will run the analytic software, the Crystalbox, to index those typical diffractograms. I will work on 3 scenarios. They are from the same sample, as you can see here. This is the austenitic nickel titanium TM foil made by FIB. The magenta circles here are SAED apertures I used to choose different areas of interest. The first example is from this grain. There is just one single lattice. The second example is from this grain. It contains 2 phases. The dark matrix and the shiny wedge is the residue after martensite transformation. So we have 2 lattices in here and 2 sets of dots in here. At last, I used the biggest SCED aperture to incorporate as many grains as possible, and we are going to index these discontinued rings. See. Yeah, so we covered 3 scenarios, 1 set of diffraction spots, multiple sets of diffraction spots, and discrete rings. If you extend the usage of those 3 scenarios, you can index most of the possible diffractograms you are going to meet. Now we know how to index diffractograms, but what the indexation of diffractograms can concretely do for us. This webinar is to unveil the materials, so how the diffractograms can do this for us. Let's go through the case studies. The first case, the electron diffraction can identify what material we are having. For example, this is the overview of a nickel titanium TM lamella. There are grains inside, and we can spot here there is a suspicious thing inside. When I first saw it, I did not know what exactly it is. But in TM, I can tilt this suspicious thing into zone axis to get the diffractogram. For the chemical composition of this thing, we have 6 possible candidates. Here I am showing the unit cells of the possible candidates. If we use these lattice parameters to index the diffractogram, judging from the indexing score, we can see that the titanium carbide is the right material composition, so that the rest of five candidates are eliminated. So then the second example is for phase transformation. If you have two or more phases inside your material, we can tilt the phases into zone axis and get diffractogram from the materials. Here, for example, we have two phases in the zone axis, and we index two sets of diffraction spots in here. We get austenite nickel titanium in -1,1 zone axis and martensite nickel titanium in -1, -1 direction. Then we can use imaging technique called dark field imaging to view where the different phases are located, so that we can reconstruct the grain. For example, here, the magenta region inside the grain is nickel titanium austenite, and the green region is nickel titanium martensite. With the help of the indexed diffractogram, we can also identify the interfaces between the two phases. Furthermore, the orientation of the phases, the indexation, the interfaces, the planes can be fed to calculation and simulation, which will help put forward the mechanism of the phase transformation. The previous example shows how indexation can feed the calculation and simulation to prompt the development of mechanisms. Here we have an example to show how electron diffraction can prove hypothesis of a mechanism. So for example, here in year 2020, Mrs. Hanush Steiner, who has been working on theoretical and applied mechanics, put forward a mechanism called quicking, which is a combination of twinning and kinking. And this new quicking mechanics cannot only exist in calculation and simulation. It needs concrete physical proof to substantiate its real existence. So we did the thermomechanical experiment to trigger the quicking process inside the materials. Then I did the TEM investigation. The whole process was very tricky because the best crystallographic direction to view the quicking process is at 010 direction. So at the very beginning, when I was making the TM foil using the FIB, I have to make sure the bulk material is correctly oriented so that the 101 direction could be achieved in the TM. Because the TM has limits of tilting, when the TM foil was made, I have to perform hunting for a specific zone axis, because from zone axis other than 010, we cannot observe the result of quicking. After I got the diffractogram from the 010 zone axis, I have to index it. And here there were multiple lattices on this diffractogram. It looks almost like rings. I have to index all the spots, making sure that there is not a single spot left behind without being indexed. So here is the indexation. There are 4 lattices, just as the quicking mechanism forecasted. So the hypothesis was thus proved. Moreover, by using the dark field imaging technique and the indexation on the diffractogram, we can reconstruct the grain. So here, the cyan area is the matrix. The green area is the 100 twins. The yellow areas are the kinks, and the magenta area is our famous 20-1 quicks. In this way, a newly developed hypothesis of a deformation mechanism was proved by electron diffraction. And the last practical case is an example of using high-resolution TEM. Because the fast Fourier transformation of the FFT from the high-resolution TEM can be used as a diffractogram. The reason why using the high-resolution TEM is because the major drawback of using an SAED aperture to do electron diffraction is the size of the SAED aperture. Look at this figure. In Telos 200, if I insert the smallest SAED aperture, the aperture diameter is 100 nanometer. If our area of interest is less than this aperture size, for example, here, our area of interest has a diameter of 40 nanometer, and our smallest SAED aperture size was 200 nanometer at that time. What can we do to get a diffractogram? The answer is to use high-resolution TEM technique and get FFT pattern. So here within this 40 nanometer circle, we have an example of partial dislocation, which creates stacking fault. So originally we have AB stacking here, and partial dislocation happens at 100 plane and changes it changes the stacking sequence into ABAC stacking. So the consequence is, due to the stacking fault, we will have a lattice that is twice longer than its origin in 001 direction. So the lattice spacing between the 001 planes will be doubled. So what change can we have in the reciprocal space? Keep the word reciprocal in mind. If we have a doubled length between 001 planes on the diffractogram, the distance between the 001 spots will be half the distance than before. And we need to concretely prove it. So what I did is to tilt this 40 nanometer circled region into 010 zone axis and perform high-resolution TEM. Let's look at this image. This area A dot I does not contain stacking fault, but this area A dot A point double I has stacking fault occurring in it. If we perform FFT from these two areas, we will get patterns that could be used as diffraction patterns. So let's look at the indexed FFT here in image A6 and A7. You can see the cyan and the magenta dots on figure A6 remains unchanged on figure A7. But on figure A7, between each cyan dot and each magenta dot, there are always extra intermediate dots marked in orange here. The presence of those extra intermediate dots just proves that the reciprocal length between 001 planes is half as before. That means the lattice has doubled the length between 001 planes. It proves the lattice change caused by the partial dislocation by using the high-resolution TEM and FFT. Another advantage of using the high-resolution TEM and FFT is to analyze dislocations via GPA analysis. The GPA stands for geometry phase analysis. So here, let's continue the previous example of partial dislocation and stacking fault. So here we have a high-resolution TEM image where the partial dislocation and stacking fault happen. We get FFT from the high-resolution TEM. What we do for GPA analysis is to select spots from the FFT and do inverse FFT in order to generate fringes of selected lattice planes. By following the discontinuity of the fringe, we can locate dislocations happen in the selected lattice planes. Here, the dislocations are marked in yellow circles. As we propose that the partial dislocation happen on 001 planes, we can see clearly that the dislocation density are much higher at 001 planes and its equivalent planes. But for other planes, there is no significant increase of dislocation density. These results obtained by using high-resolution TEM, FFT, and GPA proves the mechanism has a right interpretation of this thermomechanical process. We talked about analyzing dislocations by GPA analysis. In TEM, we can also use weak beam dark field technique to image the dislocations. Remember the evosphere we talked about earlier. In weak beam dark field imaging, we tilt the sample until the 3G dot. You see here, we tilt it until the 3G dot lies on the evosphere, so we can see the 3G dot is excited, and we use the G dot to do dark field imaging. We have a weak beam dark field image here. It was from a stainless steel, which was placed in a nuclear reactor. So neutron has been constantly irrigating on the stainless steel. The neutron can knock atoms in the stainless steel away, ending up in dislocations in the form of Frank loops. Here in the bright field image, a lot of contrasts were present, so we cannot see the Frank loops clearly, whereas weak beam dark field imaging provides the contrast of crystal defects. In this case, the Frank loops are bright, which make it much easier to be seen under the weak beam dark field condition. We are almost at the end of the presentation. We have been talking about the advantages of using electron diffraction to analyze our material, but there is also limits in this method. Firstly, it is the size of our material of interest. The largest sample we can have inside the TEM usually have a size of microns. And the material of interest cannot be smaller than our probe size, which is 0.1 nanometer. But practically, at my hands, I can promise to tilt a material as small as 5 to 10 nanometer. So for example, if you have a material with precipitates of 5 to 10 nanometer, it is still feasible to tilt them into zone axis to do high resolution TEM and get FFT as its diffraction pattern. But if you get things smaller than that, I suppose we can sit together during a TEM session just to refresh the record I have. Besides the limit of size, we also have limit in tilt. In the TEM, we got alpha tilt up to 30 degrees and beta tilt around up to 20 degrees. So for example, if you have a monoclinic sample and we got 110 zone axis when alpha and beta are both 0, but you need to go to 010 zone axis. In this case, we should tilt the alpha to 15 and beta to 30 degrees. And this request will make beta angle exceed its limit, so it is not doable. So if you would like to perform hunting for a specific zone axis, it is better that during the FIB process, we take the TEM foil from a suitable orientation based on the prioritized orientation in the material or based on the orientation map of the material. just to make sure that the specific zone axis that you want is reachable in our TEM. And the last limit is the beam damage, when you are imaging your material in TEM, beam damage and contamination happen. So if your sample is beam sensitive, we have to do TEM observation precisely and quickly. We can also use special holders to slow down the beam damage. We can use plasma cleaning to slow down the contamination. These methods are helpful, but we cannot completely avoid damage and contamination. The techniques, the limits that we are playing with require experience and expertise. Also, experiments have their own risks. But at CCEM, we are here to help, to guarantee your success. At the very end, I would like to thank my colleague Carmen and Sean for sitting with me and going through the slides and inspire me a lot. I also would like to thank my ex-research group leader, Bet, for his constructive comments during the slides preparation. And thank you, my ex-colleague Mila Klinger, for your support on the software CrystalBox. And thank you a lot, my friends in my previous research group. We're talking about the case studies in this webinar, the moments we have lived together, collaborated together, celebrated together, just have been flashing in my mind. And thank you, my audience. Thanks for your presence during this webinar. Thank you.